Welcome everyone, and today we are happy to have a talk by Marco Piva, and he is going to speak about high energy behavior of scattering amplitudes in Curies with purely virtual particles. So please start.
Okay, thank you. Thank you for the invitation, and hello everybody. So yeah, my name is Marco. I am Italian. I work in Warsaw, and today I will talk about this topic. So it has been asked me to give also some sort of introductory part. So this first part would be about this. So roughly, this is the outline of the talk. 1/3 of the talk will be the introduction on purely virtual particle, what this type of particles are, and what they are useful for, and then the main topic. So let me start with this introduction. In particle physics, I will start very broad. Particle physics, if we impose the principles of locality, renormalizability, and unitarity, we get the standard model, more or less, modulo number of particles of the same types, together with gauge symmetries. So these three principles are rather important. And in gravity, if we impose the same principles, the situation boils down to this, roughly speaking. So on one hand, we have two local theories. On the one hand, we have Einstein gravity, which is unitary but is not renormalizable. And on the other hand, we have the so-called stellar gravity, from the name of the guy who treated it for the first time, which is not unitary but is renormalizable. So it seems that there is the property of unitarity and renormalizability seems to be mutually exclusive in quantum gravity. And let's see a little bit more in detail the degrees of freedom of this theory. So what we would like to have is a theory for gravity, which is a quantum field theory, and is both unitary and renormalizable. So let's see what are the problems with this stellar gravity. The action can be reorganized in this way. And after expanding around Minkowski spacetime, we can see that the degrees of freedom are of three types. We have massless graviton, we have a massless scalar, which I label as phi, which is a healthy standard scalar. And then we have a massive spin 2 so-called ghost, which means that it has the wrong sign of the kinetic term. And this is the problematic degree of freedom, which I label as chi. If you look at the propagator of h mu nu in this action, we see on one hand that we have an improvement in the behavior in the momentum space. So this propagator falls off as 1 over p to the 4th. So this improves the renormalizability. So this is a good property. But this propagator can also be decomposed in simple fractions. And then you see these pi, capital Pi's are projectors onto spin 2 and spin 0. And you see that the term that is associated with this massive spin 2 ghost as a negative sign here. And this is the problem for unitarity. So we can summarize it in this way. If we have off-shell chi and phi, because also phi is important for this, meaning when they propagate inside loops, they are responsible for cancellations of non-renormalizable divergences, and then this is why this theory is renormalizable. On the other hand, when chi is on shell, is also responsible for the violation of unitarity. So you see that we have the off-shell properties of chi are wanted, while the on-shell properties of chi are unwanted. So we would like to disentangle these two. And this comes this idea of purely virtual particles. So in general, in quantum field theory, a particle can be either virtual or real or on shell. Just to give a usual example, a real photon in this diagram are these wavy lines. This is what we call light, basically. And while a virtual photon in this other diagram is what we perceived as the attraction or the repulsion between two charges. We would like to have, now imagine that this wavy line is this ghost, which has these negative properties, this bad property. We would like to not having this situation while still having this, because we would like to have internal lines that contribute to renormalization. However, this is, we cannot naively say, okay, let's just drop off all the Feynman diagrams, meaning all the processes that has this ghost as external line, because usually diagrams with those external lines are related with diagrams with the same lines when the same lines are internal, because of the optical theorem and also because of the Feynman prescription. Just an example here. Imagine that this blue line is the particle that you don't want, like this pin2 ghost. And you say, okay, let's just project into a subspace of the Fock space where this line are not external. So maybe basically you're imposing that this process has zero probability to occur. However, you in that Fock space, you will have this diagram because this blue line is internal, not external. And this will be non-zero, so you will get some inconsistency if you just project onto a subspace, unless you do some modification also on the right-hand side here, so in the imaginary part. So this is what we achieved with this purely virtual particle, which is for now is just words. Just describe it. So we have a prescription for, we developed a prescription to introduce this type of new particles, where consistently you can avoid to have them as external state, but still have as internal state, and contributing to renormalization. Now I will explain a little bit how this works, starting from unitarity. So I recall that S is the S matrix, and we can obtain this imposing the unitarity condition for this matrix. We have this relation in terms of T, which is usually called optical theorem. Then in general, besides this, we also have a set of identities that are always true in any local quantum field theory, which are called cutting equations. And this says that the sum is a set of diagrammatic equations, and each diagram plus is conjugated, so twice the real part, is equal to minus the sum of cut diagrams. Cut diagrams are just additional other diagram with additional Feynman rules on how to cut them. And this set of identities are always true, and if you collect them together and try to write them in a matrix form like this T matrix, you will obtain something that I could call pseudo-unitarity equation. You would obtain something like this, which resembles the optical theorem, except for this H, which can be put in this form by choosing an appropriate basis, where these minuses are somehow related to the presence of ghosts. So if your theory has ghosts or non-physical degrees of freedom of other types, you might have some minuses. So the projection I was talking before would be to restrict yourself on the space where H, on the subspace where H is the identity. But because of these minus signs, well, non-zero quantities in the rest of the space, and because of this relation, you will have those inconsistencies that I was talking about. So roughly speaking, a proper prescription to do this this consistent projection, to do a projection consistently, is to project onto the subspace, but also do something to turn these minus ones into zeros. So roughly speaking, this is what we want to do. So coming back to the example I have shown before, this will mean that this side is projected away, so we are restricting onto the subspace, and we need to put in this case, at least in this diagram, this bubble diagram, we need to put to zero the imaginary part, which because of the cutting equations is equal to the cut diagram. So this cut diagram must be 0. Now this is not a general rule, is that only for this diagram. So you have 0 equals 0 trivially. But in general, you have a bit more complicated rules. So let's start, let's see just a little bit how this might generalize. So this means that the cut propagator of a purely virtual particle has to be 0. Again, roughly speaking, cutting a propagator means that you are putting on shell this particle. So this is has some sense because we don't want this particle to be able to be on shell. So the cut propagator is 0. This means that for the case of a bubble diagram, where both internal lines are blue, so they are purely virtual, this is 0, but this is also 0 even if one particle is purely virtual, because that's the only cut you can have. In general, you might have more modified functions. For example, for a triangle where just one internal line is blue, you would have that this cut diagram is not 0 because, well, in principle, then kinematically might be 0, but it can be non-zero because it doesn't cut any blue line, while these other two are 0. So in general, you're not setting to 0 the real part of the sum of this diagram, sorry, the real part of this triangle, but you are modifying it. So in general, you might say that a diagram is modified by a subtraction, by subtracting some function, this delta n, which depends on the diagram itself and on the number of blue line that are inside the loops, meaning purely virtual particles. So for the case of a bubble diagram, this subtraction is just the real part. So we are killing the real part in the case of a bubble diagram. In general, there are more complicated functions that we've computed here, and also the general procedure is in this paper. So now, if you're not too much interested about why this preserves unitarity, which are the next few slides, you can just keep in mind, because this is important for this talk, that because I will use only bubble diagrams. So you just have to keep in mind that if you have a purely virtual particle, it just means that the real part of a bubble or the imaginary part of the amplitude is killed by this prescription. So now we'll give a brief sketch on the idea of why this is consistent with unitarity by talking about the composition for the diagrams, which was done in this paper. So I define a skeleton diagram like this. So Gn is one loop n leg diagram. The same generalization, the same decomposition generalizes for n loop, but I will talk about one loop. And I just factorize out, for convenience, some frequencies omega, which are defined here. And the skeleton diagram is nothing but the integral over the energies times this factor that I factorized before. And the good properties of this skeleton diagram, of studying these skeleton diagrams, is that they also satisfy basically the cutting equations, an equation with the same structure. But the good properties of looking at this equation in terms of skeleton diagrams is that it's possible to see that this single equation is actually a sum of a set of other equations that are independently 0. So there are many equations that are 0 independently, and when you sum them together, you get this equation. And now I will show for a few examples how this decomposition works. So for the case of a bubble diagram, you have the skeleton diagram is this one after you integrate with the residue theorem, and then you have this quantity, and you can use this formula and obtain this decomposition. So now again, you don't need necessarily to pay attention to what are all these quantity that I define. Just keep in mind that P is a principal value or a combination of principal values, so something without a pole, and capital delta are just delta. And the numbers are related to the legs that are in the loop. So this is leg 1 and this is leg 2 in the case of the bubble. And these deltas are important because these are the quantities that after you integrated over the space momenta, because remember this is just the integration over the energy, you get the threshold. So basically these deltas are responsible for having things on shell. And this is what we are trying to modify here. So we can do the same decomposition as this one in the square, in the rectangular, also for the conjugated diagram and for the two cut diagrams, and then place them in a table like this. And the table should be read in this way. This diagram is given by this coefficient times this term plus this coefficient times this term plus this coefficient times this term, and the same for all the others. So the sum of these diagrams has to be 0 because of the cutting equation. That's the cutting equation. The sum of diagram plus its complex conjugate plus all the cut must be 0. But you see that each line is actually 0. And these are independent quantities. So they sum to 0 independently. This means that if I kill, so to speak, some row in this table, I still have the cutting equations, meaning the sum of all these diagrams, even if I modify them, is still 0. So in the case of purely virtual particle, the rule would be that you have to remove every delta, because every delta is associated to a particle being on shell. Every delta that contains a number, an index, associated to a purely virtual particle. So let's suppose that in this bubble here, particle number 1, you want it to be purely virtual. It means that you have to remove all the delta that has a 1. In this case, you have 1 in both deltas, so you just kill all the deltas. And you're left with P2, and P2, if you go back on the decomposition, is the imaginary part of B, which is what I said before. So you kill the real part in the case of a bubble diagram. But still, the sum of these diagrams is still 0. You can repeat the same argument for the same decomposition for a triangle diagram. Again, I introduce another quantity, which is this Q, but it doesn't matter. Also, Q is a combination of principal values, so something which has nothing to do with particles being on shell, only the deltas are. And now again, you see that the sum of this diagram must be 0. Each line is actually 0 independently. And again, suppose that particle 1 is a purely virtual particle. Then you have to kill every every row that contains a delta with at least a 1. So if you do that, you are left with this. So you see that in this case, we have some real part surviving. And also, after you kill some rows, some of the diagrams are 0. For example, this diagram, if you look at the column, 0, 0, 0. And of course, this is the cut diagram where you cut particle 1. This has to be 0. And also the other one where you cut particle 1 becomes 0. So now we are left with a modified. You know how you need to modify each diagram, conjugated diagram, and cut diagrams in order to make a particle purely virtual without violating the cutting equations or the optical theorem. So this is more or less the main idea, and of course the main application for this was to quantum gravity, because the particle that it's annoying to be there and we want to remove is this ghost, but we want to remove it without ruining the property of renormalizability, and to be consistent with unitarity. So this is the technique we used. In general, we also studied the application of this idea to any theory, basically, because you can introduce it in this way, and also in theories other than gravity. But still, my interests are mainly on gravity. So now I will go to the main part of the talk, which is
a question.
yeah.
Suppose before quantum gravity, you suggest to modify a theory somehow. So what do you suggest? Not in terms of cutting rules, but in terms of calculating the amplitudes.
The question is, how do I calculate the amplitudes?
Yeah.
It's
change rules.
What?
How do you change Feynman rules for calculating amplitudes?
Yeah, it's this way. You have to remove this. So now, sorry. For example, here, now killing these rows tells you, if you then look at the column, it tells you what do you have to subtract to each diagram. Now,
so you modify loop contributions into amplitudes.
What?
Do you modify loop contributions into amplitudes?
I modified, yes, but this is an amplitude. A loop diagram is an amplitude.
Okay, thank
you. And now here I put even all the cut diagrams because I need to show that the sum is still 0, the sum of all these diagrams. But if you then believe that this is this generalized to every order and so on, then when you just want to do calculation, you just need to compute this row. Sorry. You just need to compute this row because that's the amplitude. Well, in proportion to the amplitude, you have a factor I.
Also, does this mean that you kind of change propagator of ghost to a principal value?
No, almost. It means that I do that after integration over the energy. So if you do that before, so if you have your propagator, like let's say the Lorentz invariant propagator, and you just substitute I epsilon with just the principal value, then you will get what is called the Feynman-Wheeler propagator, and this has problem when you do loops with this propagator. At 3 level is the same. So if I have 3 level diagram, basically I'm removing just the delta and I have the principal value. But inside loops, you need to do first the integral over the energy. So you see here, I have kept the I epsilon everywhere, even after the integration, and then I divided this into each term like this in these terms, and then for the purely virtual you kill this delta. It's like having epsilon here and putting epsilon to 0. But you have to do it after the integration of the energy. And as a distribution, this gives you 2 different propagators, and one is pathological. The principal value is pathological.
Okay, thank you.
Can I ask another thing?
Sure.
So if you cannot kind of generate your procedure just by modifying a propagator, do I understand correctly that for any diagram, essentially, you have to do this kind of tedious analysis, like studying different cuts, studying like whether you want them or not, right? Like you did here, like for triangle diagram.
Yeah, but you don't need to, again, you don't need to compute all the cut diagrams. That is just for showing the optical theorem. You know what you have to subtract, because what you have to subtract is these quantities in red, and these quantities in red are computable. But yes.
Yeah, but can you be sure that this can always be done like consistently for any diagram?
Yeah, because this decomposition. Okay, this I show you just a few diagrams, but in the original paper, which was not done by me about this decomposition, there are all the details for the generalization. This decomposition has nothing to do with purely virtual particles or not. You can always decompose the skeleton diagram in this way. So where you have things P3 in this case, which has no delta, so that doesn't contribute to any threshold, and then you have all the threshold contribution. And this is can always be done. It's pretty recursive. And so every time you do this decomposition, then you have this kind of tables where each line is 0 independently. So the consistency is that I'm just dropping lines that are independently 0. So yes.
Okay, thank you.
And okay, so let me continue. So coming back to gravity, again, taking the models I discussed before, so Einstein gravity and stellar gravity. If you look at scattering for gravitons, the three-level amplitude, for example, two gravitons into two gravitons in Einstein gravity, is proportional to S, where S is the center of mass energy squared. And this is obviously because of nonrenormalizability. This is expected since every quantity then is an expansion in powers of K square S or something like this. And so this means that above some energy, some cross-section might be big, and they might violate what in the literature is called unitarity bound. In the case of stellar gravity, you can redo the same. And what you get is that the amplitude, for example, again, two gravitons into two gravitons, are the same as in Einstein gravity. So they are not proportional or similar or same behavior. They are exactly the same. And for example, in this case, the relevant diagrams are these four. And so this is, in the case of stellar gravity, this is where the external lines are gravitons. So you remember that in stellar gravity, you have many degrees of freedom inside h mu. One is massless graviton. And so these external legs are projected into massless graviton. And so this means that this diagram is the same as in Einstein because you project all the legs into massless graviton, and then you have the same vertex as in Einstein gravity. But in this case, the external legs are gravitons, but the internal lines have this stellar gravity propagator, which is modified. And this means that there are cancellation between these three diagrams. But this can actually be easily seen if you change variables. So this theory can be written in an alternative formulation where each of the different degrees of freedom that are inside h mu can be written explicitly in terms of new fields. So you can introduce auxiliary fields, phi for the scalar and chi for the massive ghost, and then do a bunch of transformations. But the point is that what you get is the action, a new action, which is equivalent, and you have the Einstein term, then you have the scalar with this potential, which, by the way, this is the same as Starobinsky action theory. Then you have a kinetic part for this chi, which is the same as Pauli fields, because it's a massive spin 2, with a wrong term, wrong sign, because it's a ghost. And then you have all the interaction that mixes the three. Now, if you look at these interactions, you see that chi and phi, with respect to h, which is now the massless graviton, behaves like matter. So you can always have only terms like interaction terms like two matter, let's call it matter, field and one graviton, two matter and one graviton, or more, two matter and two graviton, and so on. But you never have one matter and two graviton, like in any matter matter action coupled to gravity. So you see that if you have diagram, going back to the diagram that we had before, so this diagram is the same, and then if these lines are h, then this line must be h as well in this new formulation. So basically all the contribution comes from the vertices that are here, and so obviously they are the same. So why do I say all of this? Because one can say, okay, also in stellar gravity, you have amplitudes at three level that grows with S. This might be understandable because it's not unitary, so it can violate unitarity somehow. The problem is that even if you apply this purely virtual particle prescription, this doesn't change, because this whole description that I just gave has nothing to do with the change of prescription. So the question is, can I still say something about unitarity or not, because the whole construction was to have a unitary theory, but then it seems that above some scale you have cross sections that grows with the energy, and this might be maybe a problem. So this is why what I studied in the last paper, and so I will review briefly what is usually said or written in the literature about unitarity bounds, and also explain why I think that here the problem is perturbativity, not really unitarity. For some people it's obvious, for me it was obvious, but I also met other people that had different interpretations, so I will just give a brief recap. Again, I will talk about scalars because it's easier and it doesn't matter too much if you have indices or not. So imagine that you have a scattering of two particles into two particles, and this is the cross section, and m is the amplitude. Then again, using the optical theorem, you can plug this definition inside the optical theorem for this amplitude and cross section, then you get this sort of equality, where x is the sum over the all possible final states, and you can bound this in this way. Then you can perform an expansion in the Legendre polynomials for the amplitude. Usually they are factorized in this way. P are the Legendre polynomials, and these A are the coefficient, which are S dependent because this decomposition is in the cosine. Then you use this definition of M into sigma. M was here. And then you can put both M and sigma written with these expansions inside the optical theorem. And then you get this bound. Now the equality is hold when you have a elastic scattering. So let's consider that, for example. And if you have an elastic scattering, then this equality 15 imply this set of bounds on A. Now I have a curved A, is just the old A rescaled with this function. If the masses are 0, then a curved A is A. So usually you have this bound, and people study this bound for a specific process. And so far what we said is that unitarity imply 15. And then if 15 is violated, then unitarity is violated. And this is okay. Now, what I find a bit misleading, or at least this confused me, is that what people usually sometimes say, at least in my experience, is that at this point they expand the amplitude into 3-level plus loop corrections, and then they choose some process where the 3-level amplitude is just given by A0 because you have S channels only and not T channel or U channel. So this is one case, one example. And then I have heard saying, okay, so if I put these definitions inside these bounds, and then if A0 3-level violates 16, these bounds, usually this happens at some scale, then the theory violates unitarity at some scale. But I disagree, because this is making this approximation introduces another hypothesis, which is perturbativity, where perturbativity means, roughly speaking, means that the loop correction are smaller than the 3-level, obviously, but we need to remember that in quantum field theory, these quantities are not expansions in the coupling constant only. They are expansion in coupling constant, whose coefficient are functions of, in this case, S. So you might have a small coupling because you have a perturbative interacting theory, but some function of S might grow. So perturbativity in this sense, when someone approximates M with M3 and then uses inside the bound 16 is assuming that the loop contributions are small, not only because the coupling constant is small, but also because the coefficient do not grow as functions of S. So, and this is, I call it perturbativity. So I would say that the correct sentence is if 803 violates 16 at some scale, then either unitarity or perturbativity is violated. So you might violate perturbativity in this sense. So, but on the other hand, when you have a theory which satisfies the cutting equations, and those cutting equations are the unitary ones, you cannot violate unitarity at some scale. This doesn't mean anything because the cutting equations doesn't know about how the coefficient grows, well, doesn't care about how the coefficient grows. So if a coefficient if the imaginary part of this diagram grows, it just means that also the sum of these cut diagrams grows. And because this is an identity, and this is true, is implied by locality. It doesn't really care. It just rely on the expansion in Feynman diagrams, but expansion in the coupling constant. If the coefficient grows, this equation doesn't care. So if there are no ghosts, or the ghosts are removed because of the purely virtual particle prescription, this equation for every diagram imply the optical theorem. And there are no assumptions about how this coefficient grows when you derive this equation. So I think that if a theory has satisfied a unitary cutting equation, let's call it like that, and violates at 3 level these bounds at some scale, then perturbativity is violated at some scale. So I say this because I have read even that Einstein gravity is not unitary. It's not unitary, it's not renormalizable, it has all the problems. This is not true. Einstein gravity is unitary as a quantum field theory. It's not renormalizable, that's another matter. But you cannot say that it's not unitary because above Planck scale, some function grows. The unitarity doesn't care. There is something about perturbativity that it's violated there. So to study this, and see if some non-perturbative contributions or techniques can cure this. I studied some ON models with higher derivatives. So I will talk briefly about this. I show first a standard ON model with the Largen limit, just to recall what is usually done to study the Largen limit. Then I show the higher derivative version that I've studied. So this is just n copies of a scalar field with this interaction. Usually the interaction is replaced by this, where omega is auxiliary field. So if you compute the equation of motion of omega and you plug the solution back, you get your old Lagrangian. This is useful because then the vertex is simplified in this form. And you can count the powers of n easily. And then you introduce the Toff coupling in this way, and you study the limit where n goes to infinity and g tilde is fixed. So in this setting, you have that each omega propagator gives a factor 1 over n. It's just a constant, the omega propagator, but still it is there. And gives a factor 1 over n, while each closed loop of the field phi gives a factor n. And then it's easy to see, for example, process where 2 identical field goes in other 2 identical field. So you have only S-channel diagrams. You see that the sum of all these diagrams, and this dashed means that you continue to insert bubbles, are all of order 1 over n. You see, this is an omega propagator, this dashed line, so it's 1 over n. Then this is 1 over n again. Then a loop of phi gives you n, and this gives you 1 over n again. So every time there is a loop of phi followed by a dashed line is of order 1. So you have loop, dashed line, loop, dashed line. This is all of order 1 except for the first propagator, and this is continue forever. So you can resum all these diagrams and get the non-perturbative version of this scattering at the order 1 over n, of course. So I did this for this kind of models. This is a more of a class of models, and then I choose an example. It's the same model, but I have inserted some polynomials of box in the kinetic term, in the mass term, and in the interaction term. So f and g are two polynomials of degree n and r. Then I do the similar substitution for the interaction as before with this auxiliary field. And again, the interaction is just a constant now. And I introduce the Toft coupling for each coupling. And now the omega propagator is not a constant anymore, but it has no poles because it's just this polynomial. While the propagator for phi is this one. And except for the delta, now we'll study this scalar function, which is the propagator except for the delta. So this propagator can be decomposed into partial fractions. So you see each poles. And all these AI are the residues, and they sums to 0, which means that at least one is negative. So you have at least one ghost. And then I define this function Bij, which is just a bubble with Mi and Mj in the loop. And I also introduce the Bij with this tau parameter, where tau is just in front of the real part. So you remember that if I want to have one of the two, at least one, if at least one of the two particles in the loop is purely virtual, then the real part has to be 0. So if I or j or both are purely virtual, then tau is 0. So I keep a tau there to keep track of the contribution of this different prescription. And then the self-energy of omega is called sigma, and it's just this diagram made with two higher derivative propagator, and then they are decomposed into sum of this, so you can decompose it into sum of bubbles with these coefficients. So if you study the larger S limit of these quantities, you see that the self-energy of omega is given by this. So you have 1 minus tau, and Bij1 is the first order of Bij, of each Bij, which is constant plus 1 over S. And the corrections are 1 over S squared. While the imaginary part of sigma is always of order 1 over S because there is no tau there. So here I have assumed that among these n particles, n poles of the propagator, k are standard particles. So either normal particle or ghosts, and the other are purely virtuals. So if you choose tau equal 1, means that all particles have the Feynman prescription and they are all standard, meaning either normal particles or ghosts. Then the whole sigma is of order 1 over S squared. If you keep that some particles are standard and some others are purely virtual, then the real part is of order constant in S, and the imaginary part is still 1 over S squared. This doesn't mean much, but apparently it's very important when you put this sigma inside the dress propagator. So if you resum all those diagrams that I was showing before, you get, if you just resum the internal lines, that's the dress propagator, and then you attach the external leg, so you have the scattering amplitude, the resum scattering amplitude. And the dress propagator has this form, which contains sigma here, and having these two different behavior in the large S makes a difference. So to show this, I'll just do it in an example, explicit example. So I choose these two polynomials to be these two. So explicitly, the Lagrangian looks like this one. Why I choose this? Because it somehow resembles stellar gravity, at least from the point of view of having ghosts and renormalizability properties. Of course, there are much more indices in stellar gravity. The properties of this theory is that it is okay. It's not renormalizable. It's super renormalizable, and you have if tau is 1, you have n standard particles and n ghosts with 2 different masses, similar to stellar gravity. And then if tau is 0, you have n standard particle and n purely virtual particles. It means that in this case is unitary. And then if you also remove f, so you set f equal to 1 and you just leave a standard 2 derivative theory with these derivative interactions, you have a non-renormalizable theory, which resembles also stellar gravity, because if you remove the higher derivative terms from stellar gravity, you get back Einstein gravity, which is not renormalizable. So in this theory, before to go that, I also show this just for curiosity or for fun. One can ask why don't you just do that with stellar gravity? Just to give you an idea of the amount of terms. This picture, it doesn't matter the details, but these are the first 40 lines of the three-leg vertex, graviton three-leg vertex in stellar gravity. Total lines are 790. And this is a TXT file. And the TXT file is 120 kilobyte. The 4-leg vertex is 4 mega. The 5-leg vertex is 165 mega. And the 6-leg vertex is almost 6 giga. So it's long to do calculations. To do divergent part or loop, divergent of the part of the loop diagrams at one loop at least, it's quite fast. If you have to do scattering even at one loop, you need these diagrams, and it's a bit long. So for now, toy models. And the results for the example I showed. So in the theory I was showing before with this f and g of degree 1. Again, in this case where you have 2 identical particles scattering into other 2 identical particles, the sigma cross-section is this one, which behaves like S. So this is another property similar to the case of Einstein gravity and stellar gravity. And if you resum all those diagrams I showed before, the resum cross-section has this form, where D is the resum propagator, dress propagator. And then you can keep tau generic and then choose tau equal 1 means that you have ghost, and this amplitude still grows as S. While in the case of purely virtual particle, this amplitude decreases as 1 over S. So this S made the behavior of this cross-section better. So resumming them and using the purely virtual particle prescription makes this behavior different, as expected, because as I was saying before, this theory satisfies the optical theorem, so it cannot be that it violates unitarity somewhere. Maybe it violates perturbativity, which means that you need some loop contribution to restore it explicitly. In this case, you need infinitely many loops and resum them, and this is already enough to see that the theory is fixed. And as a proof of this, also in the case of ghost, which doesn't satisfy the optical theorem, if you resum all the propagator, even though the propagator is improved because it falls off like 1 over e to the 4 as well, still the high energy behavior is not improved when you resum all the diagram. I would say obviously, because still theory is not unitary. And also in the case of the non-renormalizable case, which means F1, still also is fixed, because that case is not renormalizable but doesn't have ghost, so it means that it's unitary. So this would be the analog of Einstein gravity. So also Einstein gravity, probably resumming some diagrams, you can get a good behavior. This is quantitatively slightly different, but it still decreases. So these were just the high energy limit, but I have the full function because I have the full D. but I didn't show the formula, but I can show the plot. So the dashed line is the tree level, which grows. Purple line is the ghost, which also grows. This blue line is the purely virtual particle case, and this is the non-renormalizable case. So you see that they are the same at low energies, and then when they are supposed to blow up, they are fixed, and they actually decreases. So these bumps might have some interpretation as resonances or bound states. I don't really know which interpretation they should have. Maybe not both, because this orange one, for example, is very wide. And so maybe the interpretation of a particle being there is fuzzy. So the narrow is the peak, the more it's reasonable to call it a particle, as usual, by the way. Also, these two behaviors, meaning having a more narrow peak here and a larger one here in the purely virtual particle case or in the non-renormalizable case, is not really typical. Just changing a bit the values of masses and coupling constant, you can switch this behavior. But at least this, in some cases, you can have some narrow, and maybe this is bound states of these two phi particles or resonances. Maybe that's the best, is a better definition. And then, if you remember, there were also the bounds on this quantity A, curve A, which are slightly different in the three cases. These are the definitions, and then I also plot them. This one has to be smaller than 1, and it is, except for the ghost. This has to be smaller than 1.5, and it is, except for the ghost. And this has to be smaller than 1, and it is, and the ghost is even negative in this case. So these are for n equal 1. So even if I did a large n expansion, even if n is 1, so you don't have a large n because you have only one n, still they saturate the bound. At least the purely virtual particle case saturate, while the other one is largely fine. This suggests me that maybe in other theories where you don't have a large n version to use as an excuse to resum propagators, to resum self-energies, maybe you can just resum them anyway and still get this kind of results. So to conclude, non-perturbative resummations can cure some apparent violation of unitarity bounds in theories that contains purely virtual particles, as well as in unitary non-renormalizable theory. So if you have unitarity, you cannot violate. You can maybe violate. I mean, unitarity, I mean the optical theorem. You cannot violate it at some scale. You can violate perturbativity, means that you just have to reintroduce all the loop corrections, and then everything will be explicit again. And also shown explicitly, also, although it was kind of expected to me, that theory that are renormalizable but contains ghost cannot be cured in this way, and there are these bumps that maybe they have some physical meaning as resonances. Now the difficulties with doing this with gravity, with stellar theory, is that in that case we have both 3 leg vertices where I can just resum the graviton propagator and it's fine, but we also have 4 leg vertices, so we need a way to resum them. So there should be a way to write those vertices by using some auxiliary field, like I did in the case of large n theories, but as far as I know, I don't know even if it's possible in the case of gravity to write those things. At least to have a way to resum things. And also, there should be a way to justify the resummation. In this case, I had the large n expansion, but as I said before, since everything works even with n equal 1, maybe this can just be a prescription for the series to resum first the propagators, the self energies, when you are at some high energy scale, and then do the rest. And also the other difficulties, as I showed, are the complexity of the vertices. but this is still ongoing. Okay, and this is it. Thank you.
Thank you. Are there any questions?
Can I ask two questions?
Yes.
The first is yes. Do you have some prescriptions how to find how to write a path integral for this new theory, this PVP?
No.
Okay.
No,
so,
because I can tell you why. Because so path integral is really an Euclidean object, and then you can, by analyticity, continue the result into Minkowskian, let's say, signature. And making this, canceling these rows in the tables is equivalent to reach the Minkowski axis in a different way. So basically, I'm modifying the weak rotation. So the Euclidean path integral is the same if I have or don't have purely virtual particles, because all the threshold or all the particles being on shell is something about the real axis. So it's how you rotate. The difference is how you rotate, and I don't know how to implement that in the path integral.
Do you have a Minkowski path integral regardless of whether it kind of converges or not? Can you write the Minkowski path integral and give?
No, as far as I know, no. It doesn't mean that it's not possible to invent it, but I don't tell you.
Okay. And the second question is, okay, so you change kind of plus epsilon prescription. So the question is, does this change some causality properties of the theory?
Yes, it makes the theory acausal in a very, very short range. Of course, this depends on the mass of the purely virtual particle. So clearly, you cannot have the electron to be purely virtual. Besides the fact that we kind of observe them, not really directly, but almost. Because the mass is very small, and you would have some causality issue at scale that is 1/m. In the case of ghost, this is something very, very large, which means that this causality would be violated in a scale that is that small that is not. We don't even know if causality makes sense there.
Okay, thank you. Very interesting.
Yeah. Okay, you're welcome.
Any other questions? Maybe you could repeat again. I got confused a bit about this non-renormalizable case for DSON models. So what is it? What is it? What kind of prescription?
No, it's just that, let me go back to, yeah, so this is the model with higher derivatives, both in the interaction, but also in the kinetic term, these two terms. You can see the pointer, right?
Yes, yes.
Okay. No, because all the time I've used the pointer. It's disappointing to discover that no one was seeing it. Yeah, so the non-renormalizable version of this theory is just the one where I removed this higher derivative term. So I have a standard kinetic term, but the interaction with derivatives.
Mm-hmm.
It's just without this box over M here and here, but I still have it here.
Okay, so then the loop contributions, they diverge, right? And
yes, it's non-renormalizable.
yeah, but how do you get the answer eventually? Like you have to eventually renormalize it somehow, right?
Yeah, but I was studying the 4-point function, so I just computed. I mean, non-renormalizable means that at one loop you generate, for example, here the Lagrangian has at maximum 4 phi, right? It means that there is some, I don't know, phi to the 8 that is divergent, or you have a phi box to the 3 phi, something like that. Right? You generate something that is different from this from this action at one loop. But in those one loop bubbles, you don't. That's why those one loop bubbles doesn't produce anything that is different from what is in the classical action. But in general, you produce everything. So yes, but they don't contribute in this calculation.
Yeah. Okay. Thank you. So I don't see any other questions. So let's then thank the speaker.
Okay.
Yeah. Thanks.
Thank you.